Hello friends, welcome back to C Field Academy where we learn together from each other. So today we will discuss another video which is data structure, and we will discuss the binary search tree as part of the data structure. So let's get started. So these are the following items which we are going to discuss today. First we will start with an introduction to binary search tree. Then we will move on to discuss various operations that are possible in binary search tree, and we will discuss a little bit about what each operations are. Then we will go deep into the operations. We'll first start with how the traversal operation is, and we will see a few examples, and we'll also see the algorithm pseudocode for the traversal. Next we will see the search operation in binary search tree, and we will see examples as well as the pseudocode. Next we'll move on to see the insert operation, and finally the delete operations. For both of these we will again see some examples as well as the algorithm. Then we will see the complexity analysis for each of these operations for binary search tree, and before we end there will be an exercise for you guys to try with some with a simple problem. So first of all, what is a binary search tree? So before starting, I would recommend you to visit a couple of videos that I have already created related to the binary tree. So there is a video which we have which is binary tree and different types of binary tree and its variants, which I'll make sure to link it here and in the description. So that will help you set the background for what binary search trees or a binary tree is, in case you are pretty new to the concept of a tree. There is also another video which is the search traversal video, wherein I discuss with greater examples about each of these binary tree traversals, which is pre-order, post-order, and in order. So that is also a good video to actually look at. So first, to start with, what is a binary search tree? So if you are already aware of what a binary tree is, it becomes pretty easy to understand what a binary search tree is. So binary search tree just has one additional property other than the binary tree. What? All the nodes, in fact all the internal nodes that have children, so they have the children in such a way that the left subtree, in fact all the nodes in the left subtree are less than itself, and all the nodes in the right subtree are greater than itself. So that's an important property of binary search tree, and this property helps binary search tree basically to become a special tree which can be used in variety of applications, especially related to the computer science. And in fact this is one of the most commonly used data structure that is used for searching. All the search operations, all the operations like search, insert, and delete can be done in logarithmic time or a log-in time, in comparison to if you take an array where we have to traverse through each of the elements. This is pretty fast, and hence this is actually proportional to the height of the tree. And that's why if the binary search tree is unbalanced, which means we will see a few examples next to see what it is. So if the tree is unbalanced, the operations are still costlier. It doesn't make any difference in comparison to the normal array. So here is an example of binary search tree. As you can see, for every node, all the nodes in its left subtree are less than itself and right subtree are greater than itself. For example, let's take node 25. So if you notice, all the nodes out here to its left are less than 25, and all the nodes to the right are greater than 25. And the same property holds good for any other node. Let's take 5. 5 doesn't have any left subtree and right subtree, so it's good. Let's take 40. So 40's left subtree is 38, which is less than 40, and 40 is right subtree is 48, which is greater than 40. The same holds for every node in the binary tree. And one more important point to note here, it's not necessarily that the binary tree has to be complete, or it's also not necessary that the binary tree has to be balanced. You can see we have a node 22 here which doesn't have any children. So this is not a complete binary tree, but it's still a binary search tree. Alright, here are a few more examples. In fact, this is a BST which is skewed to its left side. It's still a binary search tree because it holds the same properties. It is a binary tree, and every node to its left, let's say all the nodes to the left of 25 are less than itself. It doesn't have a right subtree, but it still has the property of the binary search tree. Same thing with 20, the nodes to its left are less than itself. Same with 10. But notice this is a skewed tree, and in fact the skewed tree search operations won't be of any any benefit in comparison to a linear array. Here is another binary subtree which is skewed to the right side. Similarly, all the nodes to the right are greater than itself. So all nodes of 36 to the right are greater than, and all nodes to the left of 36 are less than itself. Now here this is another tree, but this is not a binary search tree. So I'll give a moment for you to think why it is not a binary search tree. Alright, let's see why it's not a binary search tree. In fact, it's the same BST which we saw in the previous slide or in a few moments earlier. But notice this guy here, notice this element 8, and notice its left subtree and its right subtree. So in its left subtree we have one node 10 which is actually greater than 8. This violates the binary subtree property. We have discussed that all the nodes to the left or the left in the left subtree should be less than itself, but 10 is in left subtree of 8, but it is not less than 8, and hence this violates the binary search tree property, and hence this is not a binary search tree. The right node is fine, but it's just because of this node 10 due to which this is no longer a binary search tree. Alright, now let's see what are the important operations that are possible in binary search tree. In fact, these operations are pretty similar to linear array, and these are useful in terms of when we use the data structure in various applications in computer science. So first of all, traversal. So traversal means visiting each node or visiting each element in the binary search tree to perform certain activity. So binary search tree traversal includes visiting nodes using recursive strategy, and most popular strategies include pre-order, in-order, and post-order. The next one is search, which means to find an element if it is present in the binary search tree or not. So the process just involves starting from the root, and then we recursively search to the subtree by first checking if the node is if the element that is searched is less than the root. Now this is where the property of binary search tree comes in handy. So if we know that the element we are searching is less than the root, we just ignore the right subtree, and then we search in the left subtree. And similarly, if it is greater than the root, then we go and search in the right subtree. Now the insert operation is very similar to the search. So what happens is we just search the element if it is present in the tree, and when we search we actually find the location where the element should be located at, and then what we do is we find the leaf, and then we compare it, and then decide whether the node should be the left child of the leaf or the right child of the leaf, and then we insert the node. And the last one, which is delete, which is a little complex to handle, but how this is done is we just replace the element by the largest element from the left subtree or the smallest element from the right subtree. We'll see each operations in detail, so we don't need to bother about if you note, so in order predecessor is nothing but the largest element in the left subtree, and in order successor is the smallest element in the right subtree. We will see this when we actually do the in order traversal in a short time. Alright, so let's start with the first operation, which is traversal. Now I want to let you guys know that I have a different video with very detailed example to explain these traversal strategies, and hence I recommend you to visit that video, because that will give a greater in-depth understanding of the traversal strategies. And now though that is the traversal strategies of binary tree, but since binary search tree is also a binary tree, the same traversal strategy applies there. So I'll make sure to link here and also put it in the description so that you can look at it. So what is traversal? So traversal is nothing but visiting the nodes using certain strategy. In BST it's usually recursive, using certain strategy. So popular strategies are pre-order, in-order and post-order. So in pre-order traversal, what happens is, if we have a node here, we first visit the root of the tree, then we will visit the left subtree and then the right subtree. In order, the root is visited in between, so which means first we visit the left subtree, then the root and then the right subtree. Whereas in the post order, root is visited at the last, which means first we will visit the left subtree, then right subtree and then the root. An important point to note is in order traversal in a binary search tree gives us the sorted list of items. Sorted means ascending order. So let's see each of these strategies in detail. So here it is. So first, as we discussed in pre-order, first we visit the root, then the left subtree and then the right subtree. So here is the algorithm for pre-order traversal. So the pre-order traversal algorithm takes the root, which means the root of the binary tree or the root of the current tree, and it recursively traverses using the strategy. Now since this is pre-order, we know that we have to first print the root. So what the algorithm does is, in the step 1 you can see it checks if root is not equal to null. So which means if the binary tree or the current part of the binary subtree is not empty, then we just go ahead and print first. And then recursively we call the pre-order on the left subtree, which means we'll pass the root dot left as root for the subtree, and then pre-order root dot right, which means the right subtree as the root of the subtree, and this process will then call recursively. So which means first pre-order root dot left will be called, that will then again go ahead and check if root is not equal to null, and so on. We'll see an example. Let's see a pre-order traversal example. So let's say this is our binary search tree which we are given, and we need to do a pre-order traversal. So first step, what it will do is it will go ahead and check if root is not equals to null. So if root is, as you can see, the value of root here is 25. So we will first see it's not null, and then we'll print root dot key, which means we'll first print 25 here. So that is the first step. As you can see, it will first print 25 over here. Then what happens is it calls pre-order root dot left, which means it will call pre-order on this subtree, and it will pass the root as 20. So 20 will be passed as the root, and in the next call 20 will be passed, and then this subtree will now be called recursively. So once this subtree is called recursively, it will go ahead and check again root is not equal to null. Root is 20 here, so 20 is not null, and hence it will go and print 20. So the next node that will be printed is 20 over here. So that's why we have next node printed as 20. Now again this will call a pre-order on root.left, which means it will call a pre-order on this part of the tree, due to which it will go ahead and call the method recursively again, and it will pass 10 as the new node, and it will go ahead and print 10 the next time. So that's why 3 is printed. Similarly, it will go ahead and call the next subtree which has only 5, and it will call 5, and then 5 will be printed. Now what happens here? It will again call root.left on 5, but root.left is here null. So due to which root null will be passed, and then in the next step this call will fail, due to which it will return. So which means after it has printed 5, it will no longer go ahead into further recursive call. It will return, and then it will return back to root.left, and it will go to root.right for 5. Now root.right is also null, due to which it will also return, and then finally this call will return back here, which is 10. So this is where after printing 10 it will return here, and then it will call the pre-order root.right for 10. So which means it will call this subtree for 10, due to which it will go ahead and next print 12, and recursive calls to its left and right child will fail. This will return, and hence it will return back to 10. Now for 10 also all the 4 steps are completed, so it will again return back to its root, which is 20. Now when it's 20, it would have printed 20 here, and then this call would have been completed. It will go ahead to the right subtree, due to which it will go ahead and then print 22, which is the 6th node to be printed, which means it will again return back, and then it will return back to 1. Once it returns back to 1, one's left subtree is now traversed, so it will traverse the one's right subtree, due to which it will print 36. But again, once 36 is printed, it will go to its left subtree, and it will print 30, then 28, then it will return back, and then it will print the 36 right subtree. It will go to the 36 right subtree. It will first print its root, which is 10, then its left subtree, which is 38, and its right subtree, which is 48. And finally, this is how the pre-order traversal works. So let's now go ahead the next one with the in-order traversal, which is pretty important traversal strategy in a binary tree or a binary search tree. So here the order is a little different. In this case the root is in the middle, which means we'll first cover the left subtree, then the root, and then the right subtree. So let's see the algorithm. The algorithm is actually pretty simple. If you compare this with pre-order, what you will see is root.key is now in between. Earlier it was up, now it's in between the left tree traversal and the right tree traversal, which means first the left subtree is to be traversed completely, then the root is traversed, and then the right subtree. Now let's see this with an example. Let's take the same binary search tree which we had, and let's start. So in this case what happens is we will start with the root, which is 25, and root is not null, so hence let me write this down, 25 here, and then it will make a call to in-order root.left. So which means it hasn't printed anything, and it will call root.left, which means 20 is called on the in-order method. So this 20 is passed over here, and due to which it will go here again as a recursive call, and next time 20 becomes the root. 20 is not equal to null, which is true. It will go to the its left subtree again, because the in-order call is again called at step 2, which means 10 will be passed. So 10 is passed again recursively, and 10 is checked over here. 10 is not null, due to which 10's left node, which means 5, is called. So let me draw it out here. Left subtree, then again left subtree, and then again left subtree. So we will have 5 passed in here, 5 will go pass, and then 5 will be passed here. So 5 is not null, which means it will go to 5's left subtree. 5's left subtree is actually null, so this will become null. So null will be passed in here, and then once it reaches this if call will fail, and it will actually return. and then what will happen is the in order call will return for 5, but then it has to print, so that's why 5 is the first node to be printed. And then we will go ahead and call in order on root dot write, which means 5's write subtree, which is also null. So this will also do nothing because null will be passed in, and then the if call will fail. So finally 5 will return back to its predecessor call, so which means it will return back to the time when root was 10. So in this case it has completed this part, and then it will go ahead to step 3, which is root dot key. It will print, which means it will print 10 next. So this is how it is, 1 and 2, and then it will call the in order call on its write subtree, which is 12. So this will result in 12 getting printed. So 12 will be get printed at 13, and this will again return back to 10 because it's both left and right subtrees traversed. And then finally we will return back to 20, wherein 20's left subtree is traversed and 20 has to be printed next because the root has to be printed in between, and then it will go ahead and print the right subtree of 20, which is 22. So 22 is printed. This will return back to 20. Now 20's left and right subtree is done, so 20 will return back to 25. Once it returns back to the 25 call, 25 will be printed because 25's left subtree is done. Now 25 is printed, and next call will go to 25th's right subtree. So when the call goes to 25th right subtree, what will happen is here also same thing will happen, because first in order root dot left will be called, so which means first the call will be to this left part of the subtree, which will call the left part of the subtree, and then finally 28 will be printed first, 7. Then 28 will return back to 30, and 30 is now the root node which will be printed, and hence 30 is printed. 30 does not have any right subtree, and hence it will return back to 36, and 36 will get printed next because 36 is the root now. Once that is done, we will go back to 30's right subtree. In the right subtree we have 40, 38 and 48, but first when it reaches 40, it will first print its left subtree, which means it will print 38, then it will print 40 and then 48. So this is how the traversal for in order is. And if you notice here, in order traversal actually results in the sorted list of items in the binary subtree. So this is actually in the ascending order of sorting. Cool. So finally the last one, which is post order traversal. Now in this case the left subtree is traversed first, then the right subtree, and then the root. So the algorithm just looks a little bit more different, which means the printing of the root is now at the end. First the left subtree is called, then the right subtree is called. So let's see this with an example. So this is the same binary search tree, and we start with 25. So first root is 25, and then 25 is not null, so this will call the left subtree first, which means root dot left will be passed 20, which will call recursively again its left subtree, which is 10, which will call 5, and then 5 will call null. Null will return back because the if condition will fail. But then since 5 will return back, so before 5 will return back, and once it reaches 5, 5's left subtree will return null, 5's right subtree will return null, so which means 5's left and right call has been done, and then finally 5 will be printed because 5's root dot key, so 5's left and right has been traversed, and hence 5 will be called first. Then 5 will return back to 10, but notice 10 is the root node here, so when we say 10 here, it will return back to the 10 call here. So for 10 call the left part is done now, but the right part is not done, so the right call is made first with 12. So 10 is not printed yet, and then we call the post order with 12, due to which it will go and call post order with 12, and it will first check post order of roots left, which means 12's left child and 12's right child, which are null. and it will return, and then finally it will first next print 12 as the second node, so due to which 12 is printed, and finally when 12 will return back to 10, 10's left hand side right subtree is done, due to which 10 can be printed now because root node has to be printed last. And once 10 is returned, 10 will return back to 20, but then 20's left subtree is done, but 20's right subtree has to be traversed first, due to which 22 will be printed next. And finally 22 will return back to 20, wherein for 20's left and right subtrees are done, due to which it will print 20. Once 20 is printed, then notice 20 will return back to 25. So for 25 left subtree is done, but 25 won't be printed here because its right subtree is there. So the call will go to the right subtree, which will make a call to 36 and that will make a call to 36 left subtree, which will make a call to 30's left subtree, and 28 will be printed next. So 28 doesn't have any children and it will return back to 30. 30's left subtree is done, right subtree is not present, and now 30 can be printed, so next 30 is printed. Then the call will return to 36. Now for 36, right subtree is yet to be traversed, its left is done, so then the right subtree is traversed, due to which it will go to and call with root node 40. 40 has a left subtree and right subtree, so first those will be printed, which means 38 will be printed next, 48 will be printed next, and finally 40 will be printed. Once 40 is done, it will return to 36. 36 left and right subtree is done, so 36 will be printed, and then 36 will return to 25. 25's left and right subtree is done, so finally 25 will be printed. So in fact the root node is printed at the end in the post order traversal. So cool, I hope this helped in understanding the traversal strategy. If not, I will definitely recommend you to visit my other video which I have specifically for traversal for binary trees. Alright, so that was the traversal operation. Now let's see the most important operations in binary search tree, which is the search operation, which means in a binary tree we have to find an element if it exists or not. So here is the process which we can follow. So it's also a recursive process. So the idea is just check and compare with the root. If the element is equal to root, then we are done. We don't need to do anything. We just return the index of the root node and then we are done. So next, if the element is greater than the root, so which means the element that we are searching is greater than the root, then we have to recursively search in the right subtree. So the whole left subtree can be ignored, so which means about half of the data we can just simply ignore because of the property of binary search tree. Similarly, if the element is less than the root, then we can ignore the right half of the subtree and search in the left subtree. And then we recursively do the same process over the left subtree and right subtree till we find the element. So if the left and right subtree doesn't exist, then we just return the element is not found. So let's see an example over here. So let's say here is the binary search tree which we had, and we need to search for the element 12. So as we discussed, we'll start from the root. So first we will compare 12 with 25. Now what we've noticed that 12 is less than 25. So which means this gives an idea that 12 is only present in the left subtree of 25 and all the right subtree can be ignored. So then which means we need to move left. So which means we need to move left to the left subtree. The left subtree has root node 20. So next we will compare 12 with 20. Same thing happens, 12 is less than 20, which means we need to go left, which means to the left subtree, and then which means we reach 10 now. So next we'll compare 12 with 10. Now here we notice that 12 is greater than 10. So which means 12 has to be in the right subtree of 10. So we will go and search in the right subtree. So as we go to the right subtree, the root is 12. In fact, what we'll see that there is a match. 12 is equal to 12, and hence we just return the index of 12 saying yeah, we have found 12 in the subtree. So notice how the search operation is very efficient compared to an array where every element needs to be compared. So in this binary search tree, almost in every step we are ignoring half of the data that we are searching. Cool, let's see the algorithm pseudocode for binary search tree. We have already seen for traversal, and this looks pretty similar to that. So the search algorithm or the search procedure takes two elements, the root of the binary tree and then the key, which means the element we are searching for. So the idea is to recursively compare the key with the root and then return the index if found. If not found, we just return -1. So here is the algorithm. So first step, as we first check if root is not null, so which means we are already in a tree where there is some elements, some data. If the root is null, then we just return -1. So then what we do is we see if the element we have found is actually in the root. So if the root equals the element, the data inside root is the key, then we are done. We just need to return root and then we are done. There is no need to search further. This is like a best case for us. If not, what we do is if key is less than root.data, so like we saw the previous example, so where if we find that the element we are searching for is less than the value inside the root, then we actually look for the left subtree, which means search with root.left. So root.left means the left child of root and then the key. Otherwise we search in the right subtree. And finally, once we have searched, we just return the index if we have found. So if index was -1, which means we haven't found any element, -1 is returned. Otherwise, if we have found, then that index is returned. And finally, if we see that in our subtree or in the tree root is null, then we just return -1. So which means if we have found, if we have searched through the tree and finally found that haven't found any element, and we see that we have reached a null subtree, we just return -1. So let's see the application of this algorithm on this subtree, and let's say we will search for an element 37 which is not present in the subtree. We have already seen the search of 12 in the previous slide. This time let's search for 37 and see how it goes. So first it will go ahead and see because root is 25 here and key is 37. Let me write it down. Then it will first go ahead and check in step 1 root is not equal to null, which is true. Then it will go to step 2 and it will compare key with root.data. In fact, both 37 and 25 are not equal, and hence step 2 will also fail. Step 3, key is less than root.data. Key is 37 and root.data is 25. So 37 is greater than 25. So this means it will not go to step 4 because this is not true, but it will go to step 6, which is the else condition, and it will call search root.right key. So which means it will call the search on the left subtree. So which, as you can see, it says move right. So search will be called on root.right. Root.right is here 36. In fact, this is a node of 36 and this is 37. So this will be passed, and this is a recursive call to the search method. So in this case 36, so these values will be passed over here and the next call will be made. So which means essentially we are searching in the right subtree again. So let me just clear this off to actually make it more sense, because this is the next recursive call. So in the next recursive call, what happens is, let me write it down here, 36 is the root now and the key we are searching for is 37. So it will come to this right part of the subtree. So notice what will happen here again. 36 is not null, but then it will check in step 2 36 and 37. 36 is not equal to 37, so it will not go to step 2. In step 3 it will see 37 is less than 36, which will also fail, so it will go to the else part, it won't go to the if part. So which means again the call is made on the right subtree or the right. So the right subtree in this case is root dot right, which is the right subtree over here, and 36 right child is 40, so 40 will be passed here, and as we notice 37 will be passed here, and then it will be another recursive call to search. So let me clear this again to show how this will look like. So we will pass 40 here, and this time what will happen is this condition will fail, this will fail. Root is less, key is less than root dot data. This will be true because key is 37, root dot data is 40, due to which it will go and to step 4 and it will call the left subtree of 40, which means it will call this part. The left subtree of 40 is 40's left child is 38, so 38 will be passed here, 38 and 37, and it's another recursive call to the search. So let me clear this over again, and this is 38 now, so let me write down 38 over here. And in this case again 38 and 37, so this will fail, this will fail, but here 37 is less than 38, so it will go ahead and call the left subtree again. But what will happen here is root dot left, which means 38's left child. 38's left child is nothing but null, there is nothing here. So null will be passed and this 37 will be passed. So this will make another recursive call. Let's see what happens with the recursive call now. Let me rub this. So in this recursive call, root will be null. I'll just write n. So since root is null, it will come here and then this check will fail. Because root is now null, it will not return, it will not go inside the if, and it will go to the else and return -1, which means 37 was not found, and then this is returned to the subsequent callers, which will pass on the same index back to the subsequent recursive calls, and finally this will return -1. Why? Because we saw that the 37 node is not present. Let's look this as a pictorial representation in the tree. Now notice we moved right, 37 is greater than 36. Now this will move again, and we notice 37 is less than 40, it will go to the left subtree. 37 is less than 38, which means we'll move left, but as we move left there is nothing present and we'll return -1. So this is an unsuccessful call. So I will leave it as an exercise for you to apply the algorithm for a call where the element is present in the binary search tree. It will be pretty similar. Cool. Now let's see the insert operation. Now insert operation is pretty similar to search. In fact, what we do is we first do a search, which means we'll first search for the element till we reach a leaf, till we find a leaf where we stopped and then we were returning -1 in the search call. Now here what we'll do is we'll insert our new element depending upon what is the value of the element. So if the element is smaller than the leaf, then we will insert it as leaf's left child, or we will insert it as leaf's right child. So this just ensures that the binary search tree property is not invalidated and is still present. So let's see an example here. So we have this binary search tree, and we have let's insert an element 43. So as we do in search, we do the same way. We'll first compare with the root. 43 is greater than 25, we'll move right. Then we will see to the right subtree, which is 36. 43 is greater than 36, we'll again move right, because that's what we do in search. So we move right, and then 43 is greater than 40, which is true, so we'll again move right, which means now we will reach 48. 43 is less than 48. Now 48 doesn't have any children, so this is where our search will stop, and then we'll compare our element 43 and notice that 43 is less, and hence we'll insert 43 as the left child of 40. So this is how the search operation is. Let's see how the pseudocode for the insert procedure looks like. So the insert procedure again uses similar way as such. Recursively compare the key with the root of the left subtree till we reach a leaf, and then we insert the element as its left or right subtree. So this is how the pseudocode looks like. So first of all, we just check if the root is null, so which means if we have reached a leaf and then we need to insert the element, now we just insert the element as the new node and then we return. Otherwise, if we see that the key or the element that we need to insert is less than root.data, which means it belongs to the left subtree, then we will call the insert on the left subtree and will return back the root, and then we'll return back the root to root's left subtree. Else we call the insert operation on the right subtree and then return its root to root's right subtree. And finally we will return the root of the subtree which we are traversing. So let's see this with an example. So let's say this is a subtree, this is a binary search tree which we have, and we need to insert 15. So first of all, what will happen is so key is 15, so let me write down 15 over here and 25 over here. So the first call will check if root is null, which is not true, and hence it will go to step 2 where key is checked if it is less than data or not. 15 is less than 25, so this indicates that our insertion should happen in the left subtree. This will call step 3 and it will call insert on root's left. Root's left here is 20 and we will pass the same key 15. So this will call the insert operation recursively over here, and let me now swap the values so that we show the next recursive call over here. So next, this is key is always 15, so 20 will be passed over here. So once 20 is passed, root equals to null will fail and 20 will be compared, so 15 and 20 will be compared, which will give us true because 15 is less than 20, so which means it needs to be inserted on the left subtree of 20. So this is how it happens. 15 is less than 25, we move left. 15 is less than 20, we move left. So in the next step, root dot left, which means 10 is called over here and 15 is called over here. So this will make another recursive call, and this will be 10 here, this will be 10. This time this call will fail. Sorry, this is 15, this is 10. Let me clean it and write it down. So root dot data is 10, 15. So this condition is not true, due to which it will go to the else condition and it will insert to the right subtree, which means it will insert over here. So 15 is greater than 10, so we will move right and then we will reach 12, and then this 12 will be passed over here and 15 will be passed over here. So this will make another call to 12's right subtree, and when 15 is called with 12, so 15 will be so in the next recursive call, let me clean this over again. So we will have this as 12. So 12 and 15 will be compared. We'll see 15 is greater than 12. So 15 and 12. So this condition will fail. It will come to step 5 and then root's right, which means 15's right is null here, will now be called, and this will be 15. So due to which it will make another recursive call over here, and notice what happens in the last recursive call. Now this is pretty interesting because this is when the node will be inserted. So root is null here, and just indicate it by n and 15. So what happens here is root is null, so step 1 will now succeed because root is null, and then it will create a new node. So remember we called root's left node here last time, so it will call a new node, and it will create a new node over here which is actually 15. So this will call 15, a new node 15 will be created, and that will be returned. And where will that be returned? It will be returned to the previous call. So in the previous call what happened was, if you remember, we had called the right subtree over here, root dot right, and at this stage this was null, this was 15, so this would have returned back 15. So 15 is inserted to root dot right, which means 15 becomes now, in this case the call is 12 here and 15 here, so 15 now becomes 12's right subtree. So in short, 15 is once 15 is inserted, it will again return back, and it will return the root now, which means 12 will be returned back to the subsequent previous calls, and finally this will return back, and at the end, once 15 is returned, the recursive calls will end, and then finally the insert process is complete. So this is how the insert process is. Alright, now let's move on to the last operation, which is the delete operation in binary search tree. So delete operation is probably the most complicated one, but it's just a little more complicated than the previous operations. So there are few cases we need to take care when we are doing the delete element in an existing binary search tree, not a binary search tree. So first of all, if the node has no child, if the node itself is a leaf, then we don't need to bother about anything, we just remove it. We'll see this shortly after some time. If the node has one child, then we just replace it with its child. Remember, we need to make sure the binary search tree property is not violated. And if the node has two children, so this is when the algorithm becomes a little complicated. There are two options. We can either replace it with the largest element in the left subtree, which is its in order predecessor, or the smallest element in the right subtree. So there are three conditions in the delete. Now let's see this with an example. Let's see the first example, which is the element where there is no node has no child. Let's delete 38. Notice 38 here actually has no children, so it's pretty simple to delete. We just remove it, that's all. The binary tree is not affected, so we just remove it. Now let's see the second condition, which means the node has one child. For this, let's take an example of 30, because 30 has one child, which is 28. So how do we delete it? We just replace it with its child. So the simple strategy is just replace 28, remove 30 and then replace 30 with 28. That's all. Now we'll see the third example, wherein the node has two different children in just a short while, after we just discuss the algorithm or the pseudocode for the delete operation. So the pseudocode for delete operation is a little complicated, but let's see, we will go through it step by step. So here is the pseudocode. So the delete operation works in a way similar to the other operations, but it has some special case to be handled. So first of all, to delete the element, what we need to do is we need to find the element, and hence our algorithm will more or less work in the same way. So first let's see if the root is null. If the root is null, then we cannot delete anything, we just need to return. Now next is, if the element that we are searching, which is the key, and root is the root of the tree, it is less than root.data, which means we need to delete an element which is present in its left subtree. So what we do is we just delete the left subtree and then we will return. Now to make sure that it's possible that even the root node itself has to be deleted, due to which we need to make sure that we are returning the correct node, and hence we assign this to its left subtree, and then we return back our root. Similar thing happens with the right subtree, which means if the element is in the right subtree which needs to be deleted, we just delete the element, we reassign back the right subtree, and then we return. Okay, cool. Now what happens if root's left subtree is null? Now this is the condition where we are actually handling the conditions. Now let's say it's the root is not null, and the root the key is the root, which means the root node itself needs to be deleted. And in this case 2 and 4 will fail because key will neither be less than root or greater than root, but key will be equal to root. Now here what we need to do is we need to check for all the three cases that we were seeing. First step, we check if the root's left child is null. So which means if the left child is null, which means the root only has one child, which is the right child. So in this case we just need to replace the left child current root with the root's right child. So that's why what we do is we remove the root and we just return root's right subtree as the root. Same thing happens if this is not true and if root's right child is null, which means the root or the node only has the left subtree. So we just return the root subtree, which will delete the current root, and it will return the left subtree. Now these were the cases wherein there were single nodes. Now what if if the element that is deleted, which means the current node, has two children? Now in this case we call a special process, which is the min value. So what this does is it finds the minimum element of the right subtree, and that is what needs the current node to be swapped with. So first what we do is we call a process min value, which we will see shortly what it does. So it just finds the minimum value or the minimum node in the subtree or the minimum node in the tree and that is returned. Once that is returned, we just copy that value to the current root, which means we will replace the value in the current node with that value. And once we have done that, then we just go ahead and delete that node, which means we call the delete on root's right subtree and the value that we found. So cool. So what this does is in few short words, it finds the in order successor, or it replaces the root node with the minimum of its right subtree, and then once it's done, it will delete that minimum node, and finally it will return the root node. Now let's see this with a concrete example. So let's say this is the tree which we have, binary search tree, and let's say we need to delete node 36. So notice node 36 is in between over here. It has left child as well as right child, so which means it's the most complicated option that that would happen when we are deleting the node. So first step, 36, let me clean this off so that it becomes a little easier. So first step is the delete method is called, and delete method will pass key as 36 and then the root node as 25. So what this will do is it will go ahead and check if root is null, which is not true. Key is less than root.data. This check will fail because key is now 36, root.data is 25. So which means 3 won't be called, but 24 will be called. Key is greater than root.data, which is true because key is 36 and root.data is 25. This means the delete value will be called recursively over here. So this delete will pass root.right, which is 25's right child, which is 36, and then the key is 36. So in short, we are moving right, and then this will make a recursive call. Let me clean this over here so that we are now sure what will happen here. So in this situation 36 will be passed as the root, and what will happen is the one will fail because root is not null. Key is less than root dot data, no. Key is greater than root dot data, no, which means key is actually equal to root dot data. So it will go, so step 1 to 5 will not be executed, but step 6 will be executed, wherein this step is executed. Now in this step it will check for root's left node, so 36 left node is not null, and hence this will also not be executed. 36 right node, which is in the next step, will also fail because root 36 right child is also not null, so this will fail, and hence the next step, which is these two steps, will get executed, wherein we find the in order successor of the node 36 and we'll replace it with that. So first what will happen is this step will be called min value. So the min value here will find the minimum value in its right subtree. Now in this case, if you notice, the minimum is 38. We'll see shortly how the minimum value method is called. So this will return min value as 38, and 38 will then be replaced, 38 will replace 36, and then 38 will be deleted. So we'll just replace 36 with 38, and we will make a recursive call to 38 with root dot right, which means the right subtree, and root dot key with 36. So a delete method will recursively be called on this. Alright, cool. Now let's see. Now when the delete method will be called here, it will actually go ahead and finally it will delete the node 38, and if you notice the min value 38 will go ahead and replace 36. Now let's see how the min value looks like. So min value is pretty simple call. What it does is just returns the minimum value that is in the current subtree or the current tree. So it's pretty simple. What it needs to do is just need to recurse and then find the leftmost leaf. So which means first it starts with 36, and so if it starts with 36, then the min value will just be, it will just traverse over again and again to its left subchild till it finds its left subchild is null, and that will be the minimum value. Same thing with 40. If let's say we take 40, the minimum value is 38. So we just traverse through left and left till we find the minimum. So always the left, recursively if we go to the traverse as the left subtree, then that will be the actually the minimum value. So this is what the minimum value is. So once again, if we go back here, we see when the minimum value is called, it just returns the minimum value in that subtree, and that value is then replaced with the element that we need to delete. Alright, cool. So finally we are done with all the 4 operations on a binary search tree data structure. Now let's go ahead and do a complexity analysis of all these 4 operations. Now the complexity analysis is also simple if you just understand how a recursive call works. So it's basically similar for all the 4 operations. So let's first start with traversal. So in the traversal of binary search tree, if you notice, all the 3 traversals are pretty similar in terms of time complexity. It's just that the order of printing is switched or flipped. So we'll just take one of the strategies and see how it looks like. So let's take the pre-order strategy. So in the pre-order strategy, what we do is we first print the root, and then we call the left, and then we call the right. So since it's a recursive call, we can easily compute the complexity by using a recurrence relation. Now in this case, Tn, if Tn is the complexity of pre-order, then if you notice there are 2 calls made to pre-order, due to which it is 2t and n by 2. Why? Because effectively what we are doing is we are halving the we are actually halving the number of nodes. That's why this has become n by 2. I mean on an average, but if it's a skewed binary search tree then this may not be true. But as on an average, if we assume a balanced binary search tree, it roughly becomes 2tn by 2 and then plus 1 because 1 is the printing operation. And if we solve this, we will see that tn is order n. And in fact, if you intuitively notice, because traversal has to visit every node and it visits every node once only, not twice, so it's actually order n. So this is pretty simple. And the same case happens for average case as well as worst case. In either of the case, it has to visit all the nodes. So that's why this is order n. Now let's see the search and insert operation. They are pretty similar. In insert, there is just one additional step to insert the node or the new element as a left child or a right child. So this is how the search looks like. So in short, what we are doing is we are just comparing the element with the root, and then we go to the left subtree or the right subtree. So every time we halve the number of elements in the binary tree, and then we do a search on that, effectively half, assuming it's a binary search tree. And that's why if you notice, the tn or the time complexity is tn by 2, which means we are effectively halving it, plus 1 for the comparison. And that's why in average case, if we solve this recursion, it's log n, which is actually pretty good compared to an array. And intuitively, if we say only the height of the tree is visited, so we just go down each level one by one, and we are just traversing the height. So we are not traversing all the elements in the binary search tree. But what happens in worst case? In worst case, actually this is no better than an array, because if you remember, if we have a skewed tree wherein there is only a single child for every node, and that single child is its left subtree, let's say, which means if it's left skewed like this, it doesn't help much. We are anyway traversing the entire list of elements in the worst case, and that's why in the worst case this is order n. Same thing happens with a right skewed tree. So in average case it's log n, in worst case it's order n. Now similarly, the insert operation, it's very similar in terms of time complexity, and hence the average case for insert is also log n, but the worst case is order n. Excuse me. Now let's go ahead and look at the delete operation. It's a little more complicated than the insert or the search operation. And if you remember, we had a min value method that was called in the delete. So let's first see what is the time complexity of min value. Now remember, the min value recursively calls the same method over its left child. And in fact, if we write down the recurrence relation for the min value, its tn is tn by 2, which means every time it just calls its left subtree recursively. If we solve it, this will give us log n, which means this is traverses through the height of the tree. Now let's come back to our delete operation and see the different calls which we have. Now in this case, there is an if else condition, and there are actually three conditions: 1, 2, 3. So the first condition is if the element is less than root, so we call the delete operation recursively. Otherwise, if the element is greater than the root, we call the delete operation with the write recursively. Otherwise, if it is equal to the call, if it's equal to the root, then we call the min value, and we will call the delete operation on its right child. So notice this min value, as we have already discussed, this is log n, which is over here. So if we solve, so what happens is it goes to either of the three calls. So in the third call, so in the first call the delete operation is called, in the second call the delete is called, in the third call case a combination of min value and delete is called. So min value is already log n, and delete on the right subtree is called. So if we solve this, if we notice, what will happen is tn, if we write the recurrence of the entire delete operation, it is nothing but tn by 2. So every time what happens is the delete operation is called on half the subtree, either left or the right, or in the last case it's actually the right, and the min value is also on the right. So the right subtree is here called twice, but because this is same, min value and delete are kind of similar, they're doing the same thing, it doesn't make any difference in terms of time complexity. So in short, every time what happens is the recurrence relation can be written as tn equals to tn by 2 plus 1. So every time we are effectively halving the number of nodes when we are deleting an element. So if we solve this recurrence relation, we will have tn equals to log n, which means only the height of the tree is visited. So it's exactly equal to the search or the insert operation. But in the worst case, when the tree is skewed, this actually ends up in the total number of nodes, which is order n, so which is no better than an array. Alright, let's just revisit the complexity of all the 4 operations. We have seen search, insert and delete are pretty similar. They are order log n for average case, which is very good, and order n for the worst case, whereas traversal is order n for both the cases, average and worst case. Awesome. Cool. I hope it was not a pretty long video. We have reached the end of the video now, and hence before we end, here is an exercise for you guys for the binary search tree. So we are given a number of nodes, number of values here over here, and starting from the very first, assuming that the initially binary search tree is empty, insert the following elements in order one by one: 9, 8, 5, 10, 12, 1, 0, 6, 4, 2. Next, search for the following elements in the BST. See how the tree looks like and what are the different steps that get executed if the element is present or not. 8 and 7. Then question which traversal produces sorted output in BST. We have already discussed this in the video. If you want to, please go back and revisit the part of the video where this was there, and show this result in the BST built above. So which means see which traversal it is and then execute that traversal on the binary search tree which we just built. Then delete the following elements in the BST, 9 and 1. So after deleting, make sure that the property, the binary search tree property, is still there. And that's all I have for you guys in this video. I hope you enjoyed the video. I would also recommend you to visit other videos on our channel, and please share, like, comment and subscribe. If you have any questions related to this video, or if you even want to communicate with me about the exercise, please do so by adding a comment on this video. And thank you guys. This is Suraj again, and I hope this video helped. Bye for now. See you again in the next video.